So thank you all for coming. I'd like to welcome David here. David coordinates a research program in the Institute for Renewable Energy at EURAC on photovoltaic systems. I know David through our work with Australia's work with the International Energy Agency. David represents Italy in the PV power systems program on performance and reliability, where the representatives in Australia are Lyndon Frierson from Logistica, which operates out of CAT Projects, operates out of Central Australia, and David Parvalut from Murdoch University, and Anna Bruce has something to do with the program as well. David's here for 3 weeks or 4 weeks. He'll spend 2 weeks here at UNSW. Next week he misses a week, and then the following week he'll be here. So you're more than welcome to catch up with David on topics of interest in the next few weeks. And David will tell us now a little bit about what they're doing at EURAC on PV performance and reliability. So thank you all for coming, and we'll welcome David.
Thank you. Yeah, thank you, Renate, for your kind introduction. David Moser, I'm from Bolzano. So I work in Bolzano, north of Italy, very close to Austria. I heard some French voices around, so you're probably more familiar with that. What is EURAC? Just a very brief introduction about the organization I represent. So EURAC Research is a private research center. It was founded in 1992 in Bolzano, but let's say the topic of renewable energy and energy efficiency was only introduced in 2005. Back in 2005, everything was started by, let's say, the idea of 4 people, and now we are more than 100. So what we do is applied research. So we do a lot of, let's say, third-party funded research through EU projects, but also directly commissioned by companies. We look at advanced energy systems and, of course, based on sustainable energy sources and so on. The Institute is divided into 5 groups. I personally lead the photovoltaic energy system groups, but there are other 4 groups focusing on sustainable heating and cooling systems, on energy efficient buildings, on energy retrofit of historic buildings, and on a larger scale on urban and regional energy systems. We have, as I said, more than 100 collaborators. We are still growing and thinking about growing more. If funding allows. We have more than 50 projects and consultancies and around 7 labs. What do we do within the PV energy systems group? What are our topics? So we deal with performance and reliability, of course. That was our key topic since the beginning, since 2005. But then we started also focusing on PV in buildings and PV in grids. Regarding the performance and reliability, at the airport of Bolzano, there is what we call multi-technology PV plants installed in 2010. Then we have something like 24 different PV technologies side by side, so small arrays of 2 kilowatt peak each. And what we do with it is a really good playground for us in playing with field inspection, in monitoring data, in doing side-by-side comparison. We also look into soil resource assessment and soil economics. We do have an impact strategy in order to, let's say, increase our outreach, mainly in Europe, but also internationally. As already been mentioned by Renate, we are part of the IEA PVPS Task 13, but also Task 15. Task 15 is focused on BIPV, Task 13 on performance and reliability. I am member of the steering committee of the European Technology and Innovation Platform, which is basically is a platform that gives support to the European Commission in terms of R&D agenda in the PV sector. We are part of EURAC, which is the Association of the European Renewable Energy Research Centers, part of a cost action, which is a very European thing, but also other countries around outside of Europe can be involved, where we cover performance and reliability, quality issues, BIPV, and grid integration. And we are part of the working group 1 of the technical committee 82, looking for norms and standardization. So there is a quest for quality, and what type of activities have been done in the past and why is quality important. So if we look at the levelized cost of electricity, if we do a sensitivity analysis, without, I don't even remember which location I selected here, probably Bolzano. If we look at the contribution of the capital expenditure cost, so the cost of your, let's say, PV modules and balance of system cost, this contribution accounts up to, for this specific case, 0.037 euros per kilowatt hours. Then we start adding the contribution from the operation expenditures, so everything that has to do with the operation maintenance phase. What about if I spend around 20 euros per kilowatt peak per year? What about if this is increased to 40 and so on? I can also look at the impact of degradation, so losing performance year by year to the LCOE. But what is really important is actually the cost of money. So if I have easy access to debt and private equity. So the question is almost like, does really quality have an impact of the LCOE if what really matters is the cost of money? In reality, there is a not so direct link, but there is a link between, let's say, how low the interest rate I can get, let's say, the interest rate I can get my equity or my debt off. This can be lowered down if I present a high quality project. So in the future, the wish is that not only for multi-megawatt peak PV plants, not only in that case, but also in smaller commercial size, industrial size PV plants, there is a thorough quality review that allows us to get access to low interest funding. So there will be every day more a direct link between quality and access to capital. And so what we want is to reduce the interest rate by providing high quality projects. We had a conference in Europe organized by the European Technology Innovation Platform, entirely dedicated on quality. The title was Quality and Sustainability of PV Systems. And you can find all the presentation online. The main outcome of that was that quality has a leverage effect. So if you have a quality project, this is at least the feedback from the stakeholders who participated to the conference. If you have a quality project, you can have, let's say, you can offset the added cost that you sustain to follow quality. Bankability is a variable concept, depending on who is the stakeholders involved in the bankability process. There is a need of a feedback loop, and this is quite important, especially because I guess most of you is involved in upstream activities, so material, new materials for PV modules and so on. There is it's very important to close the feedback loop between downstream, so when the PV modules is in the field, and upstream when the PV modules is conceptualized, designed and manufactured. So there is the need to reduce the gap and close this loop. And large-scale performance data are much needed at the moment. They are kept as confidential by the various project developers and asset managers. Probably mainly for the lack of confidence. So for us, it's been a journey so far through quality. Of course, my journey didn't start in 2000, it started in 2012. But before that, within the IEA PVPS Task 2, there was a first attempt to create a PV performance database. This was then included in the, let's say, next task, which became Task 13. I will give you a little bit of details about this PV performance database later on. The main outcome so far, let's say, in the previous part of Task 13 has been, of course, the creation of this PV performance database. There is a really nice deliverable for whoever is involved in failure review of typical failures in the field. This deliverable became quite important, let's say. And then we started to create an uncertainty framework in yield assessment. Again, I will say a few words more about that. We personally, as EURAC, coordinated an European project called Solar Bankability. It was very short, 2 years' time, but it gave us a lot of visibility and a lot of material that we could then bring forward within other projects and continuously within Task 13. What we did in Solar Bankability, we created a technical risk framework for various stakeholders. From small scale to large scale. We introduce a methodology that I will briefly try to explain to you later. But again, as Renate said, I'm around, so if you want to have more details, I'm really happy to sit down and discuss through that. What we call these CPM methodologies, so cost priority number, is basically tries to quantify the economic impact of failures in the field. We have another project, which is a network. In Europe, we have the so-called Marie Curie network, so networks of PhD students that together they work on a particular topic. This project called Solar Train is entirely dedicated to performance and reliability. So we have 14 PhD students all around Europe involved in the main R&D centers in Europe working on that. We have this cost action called Per PV that started 1 year and a half ago and is ongoing, where we will also create a performance database, hoping that we will manage to include many more systems. And recently we got a project funded, locally funded, that we call PV 4.0, is based on Industry 4.0 logics. And there is where we really want to close the gap with everything we learned in the past by creating an IoT and Industry 4.0 platform and rely a lot of big data analytics. Several publications were published in the past 2-3 years related to quality. One is from IRENA, the International Renewable Energy National Agency, and is about boosting solar PV markets. Is entirely dedicated to quality, mainly to, let's say, emerging markets. One publication about quality from the European Technology and Innovation Platform, which is also available on the EU PV website. One from Solar United. Solar United is a worldwide association, mostly including upstream members. So for them it's quite interesting to close this gap between upstream and downstream. And of course, with all the work done within the European Technology Innovation Platform. Within Task 13, in the last period, which started 1 year ago, I'm leading the subtask 2, which is linked to performance. And there we are looking into advanced diagnostics to reduce the time to detection of failures, or even to prevent the appearance of failures. We look into soiling, we look into climatic rating, and all of this is useful to improve yield assessment, so during the planning phase, and the calculation of degradation of performance loss rate. So now what I would like to introduce you is the technical risk framework that we develop in Solar Bankability. So I mentioned this deliverable before, review of failures of PV modules. There is where basically failures were described. In this deliverable you can find also how they manifest themselves, how they can be detected in the field. So you will find failure description, you will find the main mechanism and how to detect them, and an estimation on the typical performance loss that you have due to these failures. The interesting part is also, if you look at available literature and we focus only on PV modules, the majority of returns of PV modules through warranty claims is associated to what can be visually detected. So a lot of failures are probably underrepresented because visual detection only involves some, let's say, primitive tools that you can use in the field. It does not involve infrared, it does not involve electroluminescence and so on. So there could be a bias on all the statistics that you find around, a bias due to visual inspections. So the systematic use of visual inspection is very important because we can create easily a large data set of failures, but at the same time you need to be careful because the results could be biased by the technique that you use. A lot of data can come from insurance claims. Insurance claims, they look into failures and of course they cover the economic impact of failures. Other large data sets available are from, of course, field inspection, from the ticketing system of operation and maintenance operators, from insurance claims, from third-party review, and all these databases are all scattered around and they are not merged together into a common database. So we are sitting on a goldmine of data, but it's very difficult to do like statistics out of this, because each organization is very, let's say, secretive and they don't easily share the data they have. So when you look into our technical risk scenarios, you will start with an initial risk. You want to reduce this risk as much as possible through your PV projects. So first of all, you need to identify the risks to be able to prevent them. You will have to try to reduce them. You will have to try to transfer them, for instance, through warranty claims, through insurance, and so on. And then at the end, you are still left with some clearly identified risks that you will have as a PV owner, you will have to bear. And so you are left with your residual risk. What we did within the project solar bankability, those were the partners involved. Maybe partners like Tooth Ireland might sounds familiar to you, as they are a very important key player in quality assurance. We had the European PV Trade Association, Solar Power Europe. We had 2 consultancy companies, 3 based in Belgium and Axelio Solar based in Germany, and us. So the way we developed this technical risk framework, we started by the identification of risks, and we created what we called a risk matrix. So we went through the whole value chain from product manufacturing and testing through project planning, which involves procurement, yield assessment, and so on, through transportation, installation, operation and maintenance, and to the end of life of a PV plant. What we created is this risk matrix that essentially goes through the value chain and through the components that you can find in a PV system. And we listed all the possible failures. Initially, we did it in a qualitative way based on experience of the different partners. And then I will show you the methodology that we developed. We went back to the risk matrix to make sure that we didn't miss any important risk. So you will find all this information also in the website of the specific project, solar bankability. And what we did, we defined a list of failures, for instance, for modules, list of failures during product testing. So for instance, one problem could be that you have an incorrect power rating, because there are some flash test issue at manufacturer side. You will also find an attempt from our side to define the risk towards the aim is to find a common nomenclature, and I will explain later why it's important that everyone uses the same name for the same specific technical risk or failure. So the specific risk that I mentioned, so for instance, nominal power of a PV module was not correctly measured at manufacturer side, can of course create a certain uncertainty when you do an yield assessment of a PV project. Same thing goes for all the assumptions that you have in a yield assessment, so the amount of soiling, the shadow diagram that you have locally, they all can increase the uncertainty of your yield assessment. Incorrect assumption of module degradation, light-induced degradation, and so on. They could be unclear, so incorrectly applied. Then, during transportation and installation, I can have some problems that they don't manifest themselves immediately, but they become clear in a later stage. For instance, if I have module mishandlings during transportation and installation, I might not see the problems I created, like through cracked cells, for instance. Those, they become evident later on. So you can see that we have defined several types of risk, and also we have started thinking about how can we deal with each of them depending on when they happen. Then we have, during the operation and maintenance phase, we have what we call the quantifiable risk, because you have something that creates a performance loss. And so this is just to summarize all what I've said so far for the risk matrix. So the important thing here is that we need to categorize the risk. We need to have a common nomenclature. We need to be able that if you have 2 operators going to the field and they detect the same problem, they give the same name, because if you want to do statistical analysis on that, this is still important. So we have to also introduce a standardized quantification methodology. So this was the first part. We identify the risk. Now we want to assess them. We want to quantify them. Typically what you do when you go into this type of analysis, you apply the so-called failure modes and effect analysis. The failure modes and effect analysis is based on 3 parameters. So for a specific risk, you need to define the severity, the occurrence, and the detectability. So in terms, you can well understand that the way it works, you create some tables with some scores, and then you sit down around the same table and you try to agree on it. So it's very, let's say, subjective to the group of people working on that. So we wanted to go beyond this approach, which is great, this approach, but we wanted to try to standardize a little bit more. And so we created a cost-based failure modes and effect analysis. I will go through that later. The way we decided to quantify the risk, I already mentioned that a little bit before. So risks to which we can assign an uncertainty, so they will create an uncertainty on my yield assessment. So when I have a PV project and I want to calculate the producibility of the PV plants, this will have a plus minus a certain percentage. So there will be some risk that will increase or reduce this uncertainty range. And then there will be risk happening during the operation phase to which we can assign a cost priority number, and I will explain what this cost priority number is. Let's focus on the first part of risk now. So within Task 13, we published a so-called uncertainty framework. So we started studying into it without providing real case studies, but we looked into all the parameters that can have an impact on the uncertainty in yield assessments. This was published last year in 2018, and you will find all the uncertainties related to modeling and related to measurements through all the steps of conversion between the incident irradiation on a global horizontal level to tilt and so on to the production of electricity at the AC side. So if we look through the first most important one, which is the irradiance, so the solar resource assessment, typically it depends a lot on the database that you choose. So for the same location, you could look through the different database and you might find different values of kilowatt hours per square meter on the global horizontal level. You will also have global trends like global dimmering or global brightening, and this depends if in the specific site you used to have pollution or not, or if you have some sort of climate change, for example, will also have an impact on that. So there are various studies trying to cover that, and the question is that should you include it in during a yield assessment or not, because a yield assessment for a PV plant's production has an horizon of around 20, 25, 30 years, and it will be even more in the future. So you need to make sure that if you have a global trend of increasing irradiance incident to your models, you need to take that into account. Another important parameter that has an impact on the uncertainty in yield assessment is the decomposition and transposition models. So you measure typically you measure with a paranometer or a reference cell, you measure the global horizontal, or through satellite measurements you have the global horizontals that you need to go through the 2 processes of decomposing into the 3 parameters, so reflected irradiance, diffuse irradiance, and direct irradiance, and then you need to transpose this model into the tilt angle of your models. So by going through these 2 phases, you introduce some error, of course, some uncertainty, and it's not a given that the same the composition transposition model performs the same in different locations. So ideally, you would like to apply different combination of models to make sure that you can find the best one for your location. Another source of uncertainty is related to the temperature. In your yield assessment, you need to try to assess what the air temperature is at your location. Try to understand what the module temperature will be at your location. Ideally, you would like to include wind speed, because wind speed has a lot of impact on the, let's say, as a cooling effect of your modules. So here is just an example of three different monocrystalline, single junction amorphous, and CIGS modules that we have at the airport of Bolzano, how they are affected by wind velocity, so that the module temperature affected by wind velocity. This specifically is actually the so-called Ross coefficient that you use to calculate your module temperature if you know the air temperature. So depending on the wind speed, you will have different Ross coefficients to be applied, and depending, of course, on the packaging of your PV modules and the technology that you're using. Another important aspect in yield assessment is the value they include for your performance loss rate. We don't call it degradation because degradation is entirely related to material. Performance loss rate includes all the performance losses that you have at PV plant level, so not just related to material degradation. It could be to problems with cables, inverters, and everything. So if you only have problems at module level, the performance loss rate will be equal to your degradation, but it's not the other way around. So here is just a study that we published where we show the uncertainty of the estimated performance loss rate in percentage. So a typical performance loss rate is 0.5, 0.7% per year. You can see that the uncertainty, depending on the type of filtering that you use, can be of the same level of magnitude. So this is quite important to know that the value that you include in your yield assessment is affected by, could be affected by a very high uncertainty. How do we calculate it? This is just an example of a PV plant in Bolzano. So this is monthly yield. We calculate the performance ratio. I guess you're all familiar with what performance ratio is. We calculate a filtered performance ratio, so you can play around with filtering. You can only take, for instance, values at high irradiance to make sure that you get rid of, let's say, spurious low irradiance values. You make sure that you have a filter that you have to make sure that you have synchronized production and metadata. You need to make sure that you have the same shading condition of your modules and sensor. So you filter out all these values and you can replot your performance ratio. You can correct your performance ratio for temperature. So the performance ratio presented before is, let's say, point by point. Here is when you apply the temperature correction, and then typically you apply a linear regression. So this is very the simple methodology. You can apply more sophisticated, let's say, statistical analysis like seasonal trend decomposition, when you basically identify the seasonal trends and the degradation of the seasonal trend. For example, in this specific case, we have minus 0.88% per year of degradation. And what we are doing in terms of working programs in task 13 is that we have teamed up with several organizations around the world to look into the impact of the quality of the data, of the filtering that you apply, of the metric that you apply for the calculation of performance loss rate, and of the different methodologies. So in order to make sure that we had enough data for this benchmarking exercise, we offered three types of approaches. At the end, everyone agreed in sharing both data and methodologies, but we wanted really to make sure that we were as inclusive as possible. So we gave the opportunity to either share algorithms and data, or only algorithms or only data. So this is just preliminary results. We have applied this type of benchmarking exercise on 6 different systems so far at different climates, and this involves well-renowned research centers around the world. And here you can see for the same PV plant in Bolzano the calculated performance loss rate and the uncertainty using different metrics, different methodologies, and I'm happy to discuss about the details of it. There is no time, unfortunately, today, but you can see that it's quite interesting to see how it is clustered around a central value, but we don't know what the real value is. In performance loss rate, you don't know it. So this could be very useful in also finding how precise you can go, how close you can go to this real value, which is unknown. But you can also see that you have some outliers, so you could use this metric and use all the values coming out of that metric in your yield assessment, and you could be extremely wrong if by wrong I look how far away it is from all the other methodologies. So we also wanted to not only to look at data which comes from R&D centers, we wanted to look at data coming from, let's say, PV performance databases and so on. So we divided into, we define low quality data and high quality data. Mainly high quality data is data that is not, they've not been, they are unfiltered, they've not been pre-processed before. Low quality data is data that maybe you only have a low time resolution like monthly data and not 15 minutes or 5 minutes data. You can still gain a lot of insights looking through this, what we call low quality data. This is the data we are working on at the moment in Task 13. So we have 14 PV systems. We know pretty much everything about those PV systems because they are run by R&D centers. They are just not so far away from the offices, so they can be easily checked, sensors kept calibrated and so on. But then we also have 130 PV systems, mainly, let's say, located in Europe, but also a little bit in the US and a little bit in Asia. And the question that we want to answer is if we can see some climate trend. And we really want to see the difference between a system that is properly maintained. So the R&D systems for us is what is properly maintained because, as I said, you have students or researchers that they can go there every day to check if something is wrong. You know exactly what is happening. You can take the outliers out and so on. Compared to the results from normal, let's say, normal PV plants, which are normally maintained. So this is just an example of a study that we published at the most recent IEEE PVSC conference in Chicago. We differentiated the 130 PV plants data into usable and not usable. By usable, we went through the PR time series, making sure that we had enough data to do some meaningful analysis. Here is the subdivision of our system by technology. So we have thin film, monosilicon and polycrystalline silicon. And we also have 5 different climate zones using the Köppen-Geiger climate classification. So most of them, I think this is temperate climate because they are based in Germany, most of these systems. But what you can do, without now going through the meaning of every single value, you can either differentiate by technology, your performance loss rate. So if you have a lot of system, you could really see if one particular technology degrades more. If I associate all the performance loss rate to the PV modules, of course, degrades more than other. Or if you have some climate variability on your result. Within PV, we are a little bit luckier in terms of number of systems. We have something like 20,000 systems, a little bit more representative of the worldwide situation. And what we need to do here, because we only have production data, we have to find a way to collect meteor data and, for instance, by not one by one, but by let's say automatic treatment, download satellite irradiance, do the transposition to the right tilt angle, provided that we can trust the metadata of each PV plant. So tilt angle, location, and orientation. So this is very much ongoing work. The final question that we want to answer related to performance loss rate is a linear trend realistic? We started looking into one-step, two-step degradation, and so far, we only treated this statistically. What we want to do is to close the gap and try to find a physical meaning out of that. At the moment in this result, we don't have a physical meaning, but we want to go there and try to understand if something happened at material level or not. So this was the parenthesis related to performance loss rate. Let's continue through the parameters with an impact on yield assessment. We have poor design choices, like here is something that happened after the installation, so the tree was there, but maybe they installed it during winter. They didn't know a tree grows leaves for the rest of the year and cast shadow on the system. Even worse, they install a flower pot in front of the system. I will not say where the system is located, but it happens. So another source of uncertainty can be identified through factory inspections. So there are consultancy companies, they go through factories, they check everything is done with the highest quality. It's interesting to see a lot of deviation, I think around 25% of deviation, they are related to the quantification of the nominal power of your PV module. So calibration of the flash simulator at manufacturing site is a problem, wrong temperature correction, wrong temperature condition on manufacturing site, and so on. And this is the value that ends up in the datasheet. So it's very important to remark this part. So finally, you have a table where you can, both tables, they say the same things. What you have is an yield assessment that if you have the best information available for a specific site, you could say that my PV plant will produce 1,500 kilowatt-hour per kilo peak plus minus 5%, or plus minus 10%. So this is the typical range between 5 and 10, depending on the quality of information that you have available at your site. Why is important to know that from a business point of view? Are you familiar with the concept of exceedance probability? Okay, so when you do an yield assessment as let's say a PV project developer, you go back to your whatever person wants to put money on it, and you typically give a value which is called P90. P90 is telling you that 90% of the time, I have a 90% chance that the value of PV production is higher than what I'm giving you. So it's a very conservative value. P50 is 50%. So depending if you want to have an aggressive strategy or conservative strategy, you give one value or the other. How do you calculate this value? You have your yield, specific yield. You assume a normal distribution of your yield based on the uncertainty that you calculated, and then you take the value that you have at 90% exceedance probability. So here is, for instance, 3 curves that we've done in a real case. We played around with a PV plant. So we used bad quality information. We use, let's say, high quality and a medium scenario. And you can see that I could go back to my project developer and with 3 values of producibility that can be quite different one from the other. It will have a massive impact on my business model. Just to quantify it a little bit better, imagine that you not only have a different uncertainty, but you also have used a different database for your irradiation. And so you could have a difference between these P90 values given in this case where I have high quality data with a P90 value of this case where I chosen the wrong irradiance database, and also I had very poor data, a difference of 22%. So 22% in energy, and it will be a massive impact on your business model, and for you it could mean that you will not get the project funded. At the same time, you need to be careful that what you have here you can actually trust, because it could mean that you are over optimistic and then the reality will hit you. So what we did in Task 13 as another benchmarking exercise, so always using the PV plant to Bolzano because we know pretty much everything there. So we ask these partners, and there will be more in the future, Ekistica was part of it. So we gave a very bare limited amount of information because this wasn't a beauty contest. It was more like how wrong you can get in your yield assessment, and based on that to create some uncertainty scenarios and say how can I reduce the uncertainty. And so we did this exercise. This is just for your information that in most of the topics that I mentioned before, we ask each independent yield assessment to apply their own best consideration. And this is the result that we got. You can see that out of 4 partners, we got a lot of variety in results. So This is the energy yield assessment. If we look at the P50 value, we go from 1,150 up to 1,500 kilowatt hour per kilowatt peak, so a massive difference. And each partner provided the step-by-step how they calculated the influence of impact. And then we compare the long-term yield assessment provided by a specific partner here with real values. So this specific partner got it right. So these dots are real values. Here are real values average over previous years, and you can see there is well on the P50 values and between the uncertainty given by this specific partner. This specific partner got it right because had done yield assessment in north of Italy previously. So the next benchmarking exercise will be Australia. Is basically one of the system in Alice Springs. We will do exactly the same things. There we expect to find also interesting results in terms of assumption on soiling and so on. And what we want to do then is to look into uncertainty scenarios to make sure that we can explain also how you can reduce the uncertainty of your yield assessment. Here it just shows how you can reduce the uncertainty of yield assessment if you go from short time series, so if you only have 5 years of satellite data, or if you have 20 years of major data, you can really reduce the uncertainty of your yield assessment. So let's move on to the final part of the presentation. So we assess the impact on the yield assessment. We want now to introduce the CPM methodology. So how can I calculate the impact of some problems, failures happening in the field? So the CPN has several steps, but essentially is composed by two parts: the downtime and the power loss created by a failure, and the economic impact to fix that failure. So very simple. We published 2 papers in Progress in Photovoltaics. I can share them with you, where you can find steps by steps how it was done. We developed the methodology and we applied to a certain portfolio of PV plants by asking operation and maintenance company to share tickets with us. So in some cases it was easier because they had the tickets in paper form, so we offered to transform that in electronic format. In some other cases they already had their own ticketing platform, but they were nice enough to share their tickets with us. So we collected something like the equivalent of 2.3 million faulty components, and for a total of 441 megawatt peaks. So statistically representative, I don't know, but it's clearly a large database of failures. We created some scenarios, some absurd scenarios. In this case, it was just to create, let's say, how wrong it could get, the economic impact. If, for instance, you have a problem and you don't do anything about it, you leave it undetected, or if after 1 month you fix it. So we did this for, we tried to differentiate between utility scale, residential system, and so on. These are just some statistics. So out of all the cases that we had, we basically see that per year we have 10% of the modules have problems, 10% of inverters have problems, more or less, including soiling and shading. So not necessarily materials degradation, EVA discoloration, or glass breakers, or so on. So if we take away soiling and shading, this failure rate will decrease by a lot. Same thing we did for inverter. Main problems of inverter is overheating of inverters. And we did it for all the components of a PV plant. And then we plotted the data and divided into the cost of repairing a system and the missing production. In case of PV modules, it's obvious that it costs more to, let's say, fully replace a PV modules than leave the PV modules there with a problem, but you need to be sure that this problem doesn't evolve in the future and doesn't pose an health and safety risk. We also did an analysis by, instead of normalizing over the overall portfolio, we normalized only over the affected plants. Why is this important? Because there are health and, let's say, safety-related problems that do not appear, like theft of modules is a problem in some location, fire, and so on. If you only consider for the normalization the affected plants, then they become important, and theft of modules goes from 0.08 euros per kilowatt peak per year to 34, for example, and PID goes from 6 to 114. So when they happen, they cause a lot of problems. That's the message. We did the same for inverters. In case of inverters, missing production becomes more important than the overall cost of repair. And so this was basically the way we identified and assessed, and then we went through how to mitigate and transfer this problem. The mitigation is simple. Let's say you need to put some money on the table to do extra testing or to introduce some mitigation measures, and this mitigation measure will have an impact. So they will reduce the risk, but you will increase somehow the capex and the opex, depending when the mitigation measures happen. We only introduce a simplified methodology by introducing 8 mitigation measures, going from preventive, so before the PV plant is installed, component testing, design review by a third party, qualification of the installers, very important, and then we looked into corrective measures. So when the problem is already there, how can we fix it? So by having monitoring systems, advanced or basic, by having advanced inspection or visual inspection, and by spare part management. And this is what we get. So those are the results in euros per kilowatt peak per year by using our own, let's say, very strange scenarios, the scenarios where nothing basically is done. But we can, through mitigation measure, we can take this down from 100 euros per kilowatt peak per year down to 20 when we applied mainly the preventive measures, which is pretty obvious. If I can reduce the number of failures by increasing the quality during PV plant planning, this will have a higher impact than having already a poorly designed PV plant and trying to fix it. But when you have a very properly high quality designed PV plant, then the corrective measure has an impact. So it's important to have a monitoring system rather than not, and so on. Final touch, if you stay with me for 2 minutes more, is we try now in the last project to go from theory to practice. And we have this new project called PV 4.0. So as I said, it tries to couple Industry 4.0 concepts. So the idea of Internet of Things, use of IT devices, using on networks, cyber physical system, and so on for the PV sector. We want this project to look at both medium-large PV system, but also residential. Of course, you cannot offer the same solution, but we want to make sure that also at residential level there is some sort of awareness in what is happening, and also in keeping track not only on performance, but keeping track of maintenance logs, for instance. The overall objective is to create an effective management of the activities involving various stakeholders. And just to give an example, if before you didn't have a monitoring system or you really had just a basic monitoring system, instead you will have advanced diagnostic based on big data analytics and so on. If before, for the time to respond to a problem, you had to understand what the appropriate action, you will have instead a decision support system that will tell you, I will do this based on historical, let's say, data. Instead of assessing the situation only once you are on site, you can use the decision support system to optimize spare parts management, or to say, don't go now, go in a month's time because that problem is not so severe, so go through next periodic maintenance. And the way we envision is to be able to see your PV plant, you click on a component, you have all the logging coming from different databases that I mentioned before. You will have your laptop or your tablet or your mobile phone. You will go to the plant, you will identify the problem, you will click on the component, you will say, I've done this, this, and that. You will use a common nomenclature instead of writing in a free field. So everything will be done in order to be able to do deep statistical analysis. For this specific case, deviation was detected. There will be some clever algorithm running in the background using the CPM methodology that I explained before, and it will, for instance, we suggest to send an operator. And ultimately, what we want to do is to collect all the databases information that I mentioned during the presentation. So collecting data sheets, procurement data, yield assessment, quality assurance, ticketing system, field inspection, performance data, decommissioning data into this platform provided by our ICT partner, which is called Antares. And we hope that by doing that, we will be able to provide, let's say, a new service to the sector. And with this, I thank you for your attention, and I'm available for questions if there are any.
So do we have any questions for David? Yes. So let's start here with Jose.
Oh, okay. I have too many questions, so maybe we can meet later. Though.
Yeah.
But I have one particular about glass breakage, which is not discussed a lot in the area. But I don't know if you have data of is that glass breakage due to handling and transport or thermal stress on installed panels?
A little bit of both. Let's say that the data we have from the tickets, because it's not something that we have done it directly, and this is another problem. That's the reason why we have the we created the last project, is to make sure that we don't lose this type of information. Is that the operator goes to the field, and in the best case scenario they write glass breakage. In the worst case scenario they write problems with module. They don't really try to understand if it's due to thermal stress, if it's due to the use of metallic clamps instead of plastic clamps and so on. It would be possible to understand it by looking at the type of cracks that you might have under the module if they were generated during installation. But if we had the information, we could say, look, glass breakage during installation is, I don't know, 50%. If you apply some quality assurance in between, like electroluminescence campaign, you could reduce your problems in the future. Or you could just say, you could send them back and get a new batch of PV models. So short answer, we don't have the statistics, but we would really much like to have it. And I think it's possible to have it by standardizing all the data collection.
Let's go on in case we might get thrown out at 1 o'clock. So let's take another one.
Yeah, thank you for your talk, David. It was really great. I agree with you when you said that there's a need to close the gap between upstream and downstream, and especially when we do performance loss or degradation studies on the field, your initial point is not really your initial point, right? It's like maybe already 1 month in the field or something like that, and that is a problem when you look at on the bank side, because the promise of the manufacturer is not exactly what you're going to see in the field directly. So do you think there's a way to kind of connect with those partners to have like a feedback loop directly into the production line data to the field data, or is that too private data to get access to?
I'm afraid it's the second, so it's too, it's too private. But if you can somehow convince people with data that they have a benefit in sharing, and that's what we are hoping to achieve by all these activities, and we see some, let's say, not directly manufacturer, but people working with manufacturer, they are understanding that it's quite important for them. But the point is that both inverter and module manufacturer, they have so much data inside, they believe that they can live with that without sharing with other partners, because they do. Another way of closing the gap will be to develop new, let's say, analysis in climatic chambers, extended climatic chamber testing to make sure that you don't even have to put the module in the field, to really reduce the feedback even more.
Okay, back.
You said that the data could be biased because it's only visual inspections. Is there anything that you can do to remove that bias or anticipate what it is?
Yeah, it would be to introduce more, let's say, infrared results from infrared imaging, from electroluminescence into the database. But this is a problem that everyone has. So usually data coming from visual inspection, they can be available. In Task 13, we have a lot of data coming from visual inspection. NREL developed a visual inspection sheet that can be used. We used it in Task 13, but it's entirely based on visual inspection. So now operation and maintenance operators, they tend to use, for sure, infrared imaging, maybe they will start with electroluminescence in the future, and let's see, we could cover the bias. At the moment it's very difficult. You just need to be aware about of it. I'll give you an example. I didn't show the difference of the results of our CPN methodology for utility scale and residential. If you look at the residential systems, you don't see anything material related. You only see, I don't know, problems with modules or soiling or whatever. This is not because the problems are not there, it's because they don't even do visual inspection. And in utility scale PV instead, you do have it. So we can use the results of utility scale to go back to residential and say, look, it's likely that 20% of your modules will have this problem. So you need to do something.
Any other questions? If not, then I'd like to ask you to help me thank David for coming.
Thank you.